x.
Very good, because it's t here, and in parentheses,
and
yes.
Sine.
Yes.
1 minus 2x.
Exactly. Times, because this is not plain x.
-2.
Exactly. Awesome. Plus. Awesome. Same thing. 1 plus 2x sine 1 plus 2x times the inner function prime, which is 2. You can leave it alone. Done. Okay? So we differentiated this function that is a sum, or if you want a difference, it doesn't matter, of two integrals of functions given in a form of an integral. Okay, so in order to finish up this section and move on to the last two, let's choose any definite integral to illustrate part 2. We did that, but with several examples last time. But let's also look and see if we want to illustrate with any function. Anything you want from here. I'm going to go slowly from 25 through 54. So let's choose one more to illustrate part 2. How to evaluate a definite integral and get the number. If we need to, we can choose more than one. We're going to have plenty in the last section. Plenty more. Anyone?
What about number 47?
47. What was the other one? One was 47 and the other one was? I thought somebody else chose one. No? Okay. Good, 47. So we have the integral from 0 to 1 from x to e plus e to x dx. Perfect. It's a definite integral. I know the answer has to be a number. I have to make sure that this function is continuous on 0, 1. This is a polynomial function, continuous everywhere. E to the x, friendly function, continuous everywhere. So then no issues here. So this is, I know it looks confusing, but this is x to a power. So it's x to e plus 1 over e plus 1. And which function prime is e to the x? We know that's nice, e to the x from 0 to 1. So then I plug in 1. So 1 to e plus 1 is 1. So this is 1 over e plus 1. I plug in 1, so plus e. But now minus, when I plug in 0, well, but this is 0, fine. But when I plug in 0 here, I get 1. So then the answer is 1 over e plus 1 plus e minus 1. You can find the least common denominator and simplify it further, but that's good enough. Are we okay? Do you think we need more examples of definite integrals? Let me know, please. If not, we'll move on to the last two sections.
I think I'm good on definite integral.
Okay, we're going to have plenty more today when we get to the last section of this chapter. Okay, perfect. So we're moving on to 5.4. Which page am I on? 5. Okay, in 5.4, we're going to look again at indefinite integrals, but there is one important theorem here. Something called the net change theorem. Net change theorem. And let me refresh your memory on something we did a long time ago in chapter 3. We had a particle, and the particle was doing this. And at some point in time, we were asked two questions. Displacement. So I'm going to say this is T1 and this is T2. So at the time T1, the particle starts going to the right and then goes to the left and then comes back. And this is it. That's between T1 and T2. So what is the displacement? The displacement is this distance. It's a number. So it started at this point and it ended maybe a foot to the right or 1 inch to the right or whatever. So this is displacement, which can be positive or negative. How can it be negative? Well, if T2, let me give you an example here. If this is T1 and this is T2, the initial and the end, this will be a negative displacement because it's to the left of T1, of the point T1. Initial, ending. Okay, so this is the displacement. So that was one thing. The second thing that we looked at for this particle was the total distance. And at that time, we did this. I'm going to copy this figure. I don't want to put more stuff in there. So this is my T1 and this is my T2. So what did we do? So we took this distance because it was positive, but we still put an absolute value next to it. Then we took this distance and we put the absolute value next to it. And then we added this distance and we put the absolute value to it. So the total distance was this, which is positive, this, which is negative. That's why we put the absolute value. And then this was positive. Well, however, now we have something that we just studied. The total distance will be the integral from T1 to T2, from the initial point or time to the ending time, from the absolute value of the velocity, of course, dt. And it does exactly what we did then, but I didn't tell you. But now I can, because now we have the technique. We know how to find a definite integral. We know how to find the absolute value of a function and split it into pieces or whatever we have, right? So we don't no longer need to do this. The absolute value between this point minus this point, plus the absolute value between this point minus this point, and plus the absolute value between this point minus this point. No, there is no need, because now we have the net change theorem, which is this. I would like us to practice. I would like us to practice finding the displacement and also the total distance covered by whatever particle, if you want, from T1 to T2 using the net change theorem. Of course, remember this has to be a continuous function on the given interval. Okay, so that's what I would like to practice next. And I want to go to 5.4 here. Net change theorem. Okay. We're going to look at these integrals. They are indefinite integrals. We're going to practice as much as you want. But I just want to illustrate now the net change theorem. Nothing sophisticated, just the same idea on velocity, acceleration here. The velocity function in meters per second is given for a particle moving along a line. Find the displacement and the distance traveled by the particle during the given time interval. So I'm going to copy 69. So we have V. Oh no. Can you hear me? Can you hear me? Is it clear?
Yes,
Yeah, I can hear you.
It
Okay.
cuts out sometimes, but for now, you're fine.
Oh, if you cannot hear me, I can unplug everything and then let me know.
I think it's just lag on. Maybe it's on my end.
Okay.
But you're fine now.
Okay, let me know. Please stop me anytime. Okay, so first we're asked to find the displacement. And I should have written it here. The displacement is the integral from t1 to t2 from v of t dt. No absolute value. That's why the answer can be positive or negative. Good. So for the displacement, we have the integral from 0 to 3 from 3t minus 5 dt. It will tell us whether, if it started here and here, it ends here. This is the distance, not the distance covered, but the difference in position. It can be here or it can be here. Okay? If it's to the left, I'm sorry, to the right of the initial point or to the left of the initial point. That's all it will tell us. Okay. Oh, I know how to differentiate, to integrate this. I have 3t squared over 2 minus 5t. Why? Because the derivative of this is 3t. The derivative of this is negative 5. Of course, from 0 to 3. So I'm going to go to the next page. Luckily, when I plug in 0 is 0, so I only have to worry about plugging in 3. So when I plug in 3, I have 9, so that's 27 over 2 minus 15. So that's 30, so it's negative 3/2. And that is in meters, which means that the particle started here, and whatever it did, it ended here at a distance of, I shouldn't put minus, but I have to, 1.5 meters to the left of the initial point. That's all it means. So its position was here and it ended here after doing whatever. Now, stop me if you have questions, please. So now for number 2, for the total distance, I have the integral from 0 to 3, but from the absolute value of 3t minus 5, which is a different story. Now, we have to work on the absolute value first. Can anyone remind us what does this equal to? By the fundamental, and not fundamental, by the definition of the absolute value. Formal definition, I meant to say. By the formal definition of the absolute value, what are the options here? For any absolute value, what are the options?
Uh, 3t minus 5.
When 3t minus 5 is greater than or equal to 0. I'll move 5 and divide by 3 because I don't need this. I need this. Awesome. And the other option? Well done, Quinn.
Negative 3t minus 5.
But plus 5. Because if I put the minus in front, I have to distribute it to both. I don't calculate anything what is not here. It must be here. Do not ever write anything here other than if this is to the right of 5/3, this must be to the left. Good. So then my integral then is a sum of 2 integrals. Which integrals? Anyone? Please?
0 to 5 divided by 3.
Excellent. And from 5/3, obviously, to 3. Awesome. Of course, I have to have dt, but now I have to identify the two functions.
Say 3t minus 5.
Yeah, careful. It says less than 5/3. This is less than 5/3. So it's negative 3t plus.
3t
Yes.
plus 5.
Yep.
Okay.
We always have to be very careful because we cannot copy. If we copy reverse, then it's not going to give us anything. Good. Okay, so now we know that this is negative 3t squared over 2 and plus 5t. We've done that before. From 0 to 5/3 and plus, 3t squared over 2 minus 5t from 5/3 to 3. Sorry. Good. So now I plug in 5/3, which is ugly. Negative 3/2 times 5/3 squared, 25 over 9 plus 5 times 5/3, 25 over 3. Luckily, that's why I love to have a lower limit of 0. I don't have to plug it in. Okay, and then plus, so that was the 27/2 minus 15, but minus, careful now, put parentheses because you may forget to distribute a negative sign. So 3/2 times 25 over 9 and minus 25 over 3. Okay, so it's 3/2 and 25 over 9, and here I have 25/3. And then I will calculate this, which is not friendly. And also will show you how to do this with a calculator. Let me see, I'm on